Okay, good morning, everybody. Thanks for slogging in this morning. I think my 15 minutes of fame is over. Things are quieting down a little bit, so thanks for bearing with me on Tuesday and finishing a little bit early. We can focus now 100% on evolutionary robotics. As promised last Tuesday, at the beginning of every class, I'll put up our schedule so you can see where we've been, where we are, and where we're going. We will finish up lecture one. We've covered all the logistics. We'll finish our discussion about why it may be of interest and utility to study and build autonomous machines. And then we'll spend most of today taking a very crash course through the history of AI. We could obviously spend the entire semester talking about the history of trying to create smart machines. We're going to touch on just a few major developments in the history of AI that are going to be relevant for our discussion of evolutionary robotics. Hopefully everyone has started in on assignment one. How many of you have already finished assignment one? I think about half. Okay, that looks good. For those of you that have started and are having installation issues, be sure to see the TA. If the TA cannot help you, come and see me. If you cannot install the simulator, you cannot finish assignment one or any of the other assignments. So make sure you've got a stable version of PyroSim running on your machine. Yes?
Will the TA have hours on Monday, even though it's a holiday?
That is a good question. I don't know whether she'll be here working in the lab. Okay. Send it to us an email. If she's not, you can usually arrange to meet her at some other time. Okay. Yeah, good question. Any other questions about assignment one? If you finished, for the undergraduates, if you finished assignment one and you want to continue on with assignment two, it's already available. So go ahead and get started on assignment two if you like. Any questions about the assignments? You've already had a quiz due last Tuesday. As I mentioned, there's always a quiz due at 11:59 p.m. on the night that we have a class. So there'll be a second quiz tonight on the material, the lecture notes, and the reading from lecture two today. All good? Okay, so back to lecture one. I think we finished last time by talking about the reason why you're taking this very roundabout way of submitting assignments. If you look at the subreddit this morning, you'll see there's lots of submissions already for assignment one. Some of them are from you all, and some of them are from the online students that are taking the online version of this course. Okay. Sorry, last bit of logistics I wanted to talk about was the final project itself. We'll talk about this again in more detail when we get there. For the undergraduates, you'll have the last 4 weeks or so of the semester to take the basic evolutionary robotics algorithm that you will have running on your own laptop, which will be finished when you finish assignment 10, and you can then adapt that in different ways to create your final project. And you got lots of opportunity here to be creative. I will give you a list of idea projects, but you can also propose your own. I suggest you just pass that by the TA or myself just to make sure it's something that's doable in about 4 weeks' time. Okay, so here's some examples of things that I've proposed for students in the past, given the same evolutionary algorithm, neural networks, and evolving robots on your own laptop overnight for about 8 hours. If you create two different robots, a 4-legged robot and a 6-legged robot, does the evolutionary algorithm have an easier time evolving a neural network controller for one of those robots than the other? Is it easier to find a fast moving gait automatically for a quadruped than a hexapod? What do you think? Just given what you know about 4-legged and 6-legged creatures, what might make it easier for evolution to figure out how to coordinate the legs and move a 6-legged or a 4-legged machine faster than the other?
I think with the 4 it would be a little bit faster because there's less moving parts.
There's less moving parts, right? So one advantage of the quadruped is that there are less parameters in terms of the neural network controller for evolution to fine tune. We'll talk about sort of the space of solutions that an evolutionary algorithm is searching. We'll talk about that later. But intuitively, it makes sense that there's a smaller space of possibilities for the quadruped than the hexapod. So maybe the quadruped will end up moving faster out of 8 hours of evolution than a hexapod.
I think the hexapod might move faster because there's less room for error. Like there are more legs to catch it. So
There's more legs to catch it. If evolution discovers an okay controller for the quadruped and then introduces a mutation, there's a much higher probability that that mutated neural network controller in the quadruped will cause the quadruped to stumble than in the same situation in a hexapod, right? So there's a potential advantage for the hexapod. So you can sort of see where we're going with this. It's not immediately clear which outcome is more likely than the other. So you might spend the first 2 weeks of this 4-week period setting up a 4-legged robot and a 6-legged robot. And then in the remaining 2 weeks, one night you evolve controllers for the quadruped. The next night you evolve controllers for the hexapod. The third night you go back to evolving controllers for the quadruped. Fourth night, controllers for the hexapod, and you'll start to generate increasing data. And by the end, you might be able to show us on average which is easier for the evolutionary algorithm. Right? That's kind of the idea. Okay, you can read the rest at your leisure. I put in some links to the lecture slides here for some more interesting projects from years past. This is one of my favorite, the billiard bot. You can imagine it took the evolutionary algorithm a fair bit of time to find that neural network controller. Not bad. Here's another project.
Wait, sorry, I have a question.
Sure.
In the last one,
Yep.
did they evolve it on like different configurations of the balls, or was it the same one?
I don't remember the details, but if you click on that link, you can watch the full video, and I think there's more details in there. Yeah, good question. Okay, so this one obviously is also an object manipulation task, which, as you can imagine, is sort of non-trivial. These plots are showing some sensor data. Here are some outtakes from an evolutionary algorithm in progress. And there you go. There's a good solution. Okay, so those by clicking through some more of those links, you can get a sense for the kinds of things that are possible here. Okay. All right, so back to why robotics. Last time we talked about the field of robotics in general, why it might be useful to try and create autonomous machines. We're going to speak, obviously, in this course about evolutionary robotics. So why would we try and create an evolutionary algorithm to automatically design an autonomous machine for us? Why not create one by hand using teams of human engineers? There's several reasons why. The first one is that even if we build the body of a robot, like the nonaped that you see here, which is a 9-legged robot, even if we build by hand the body, it's very non-intuitive to see how to program it to produce useful behavior. So probably no one in robotics would argue that no one is going to go in and hand design a neural network controller for a robot. It is a very non-intuitive problem. And I'm going to use the nonaped to motivate this. The nonaped that you see down here in the bottom left is built from 2 Stewart platforms. And the Stewart, there's a little animated GIF here showing you how a Stewart platform exists. It's a little difficult to see in this GIF, but there are 1, 2, 3, 4, 5, 6 moving pistons that attach these two plates together. And as these pistons decrease and increase in length, they change the relative position and orientation of the plates relative to one another. Given what you've seen here of a Stewart platform, what would happen if you compress all of the pistons simultaneously? You decrease their length to their minimum length at the same time. What happens to the plates? They get closer together, right? That's pretty straightforward. If you extend them, then obviously the plates move apart. But any other combination of the movement of the plates, even if you try and run the simulation in your head, it's a little difficult to see what the actual relative change in the two plates will be. Okay, so in the nonaped down here, we take one Stewart platform and we attach another Stewart platform to it. And we now have a total of 12 pistons. And we're going to try and control the nonaped to, in this case, move from the left side of its wooden cage to the right side of its cage. We have 12 pistons. We're going to assume that we're going to control this not with a neural network controller for the moment. Let's simplify things. Let's imagine we're going to create a binary matrix like you see up here. And this binary matrix has 12 rows, each one corresponding to one of the 12 pistons. And each column is going to correspond to a short time period, let's say 1 second. So at the first second of movement, the first piston is going to extend, the second piston is going to contract, the third piston is going to extend, the fourth piston is going to extend, and at the next second, the pistons are going to perform these actions, and so on. So far, so good? Okay, so if we wanted to manually design a controller for this robot, the task is, if we want the robot to move as quickly as possible from the left to the right side of the cage, we have to fill in the values of the matrix. What are they? Not an easy task at 8:30 in the morning, not an easy task at any point, right?
It might be doable if you had a digital model that recorded the positions of all the pistons, and
Yep.
you moved it through the walk cycle you wanted it to do and recorded each frame.
You could, right? So you could create a digital marionette, right? So we make a model of it, and then we move the robot in the way we want it to move, and the model spits out the numbers for us. We could do that. Yeah, that's a good point. Yep.
Could use some sort of kinematics where you would give a coordinate and the robot would go. That would require more.
To give coordinates of where we want the robot to go,
Yeah.
still a difficult thing to do, right?
Because you need to do a lot of computations
That
for the power kinematics and reverse kinematics.
exactly. So for the engineers in the room, this is a very difficult inverse problem, right? Okay. So as you can imagine, when we worked on this project, we didn't actually write down the numbers for the matrix. We used an evolutionary algorithm. And the evolutionary algorithm generated these numbers. The evolutionary algorithm created a large population of binary matrices. We downloaded each matrix, one after the other, into the physical nonaped. There was no virtual nonaped here. And we let each controller control the robot. We measured how far the nonaped moved, downloaded the next matrix, rinsed and repeated over many days. This was a physically exhausting experiment to be involved in. And at the end, we got things that looked like this. attempt by the evolutionary algorithm. This is the nonaped stretching, warming up. Oops, sorry. At this point, when we saw these, we actually did start to get an intuition for how you might build this matrix. This one, not so much. So now the evolutionary algorithm is finding gates faster than we could through human intuition. Okay.
That's something you worked on.
This is something I worked on. So this was a project for NASA, and they were interested in this particular design for a particular reason. Why? It can't flip over. So the rovers that are on the red planet at the moment, if they ever enter a crater and start rolling down the edge of the crater, it's game over, right? So like we saw with the tensegrity robots, on Tuesday, NASA would like to be able to send probes that orientation doesn't really matter. They can roll and tumble and carry on with the mission. This is one early idea that we helped out with. Okay.
How come you didn't do any virtual simulation stuff? Was it just before?
So the reason why we didn't do any virtual simulations of this robot, as you can probably recognize, the dynamics or the movements of the robots are pretty complex. The robot itself is complex. One of the big challenges, which you will have hands-on experience with, is trying to simulate a complex mechanical device and make sure that it is stable in a virtual world like a physics engine. This is a non-trivial problem and is still an open challenge in the field. We might be able to evolve very sophisticated virtual robots, but they often exploit details or inaccuracies in the physics engine that don't exist in the real world. And if we go to the considerable time and expense of actually manufacturing some of these evolved virtual designs, they do not do in reality what we saw in virtuality. It's called crossing the reality gap, and we'll spend a fair bit of time talking about it in about a month's time. Okay. So there's one reason why we want to automate the design of the controllers. In evolutionary robotics, we're going to use an evolutionary algorithm to design the controller. It turns out that it is also often difficult. It is also difficult to come up with the right body plan in a lot of cases. So the nonaped, which was made of these two Stewart platforms, a lot of human ingenuity went into this problem. If we want a robot to perform a specific task, it is not always immediately obvious what the mechanical structure should be. So again, going back to the example of NASA, NASA goes back and forth between thinking about sending legged probes or wheeled rovers or drones or crawling robots. We don't know a lot about the surface conditions of wherever they're going to send a probe, so it's not immediately obvious what the right body plan should be. So one of the main distinguishing features of evolutionary robotics compared to other branches of robotics is, in many cases, you'll see that we're going to expand the breadth of evolution and allow it to tinker with the body plan as well as the controller. In the tensegrity robot example, in the nonaped example, those body plans were sort of unorthodox, but they were still designed by human engineers. Here's an example just in a virtual space where the evolutionary algorithm is designing the body along with the controller. They're not very obvious body plans. You'll notice some of the elements of this robot are black and others are white. Objects that are black have no neural control inside, so they're kind of like bone or a passive support. And the gray spheres that you see here have some neural structure in them. Here's a design which for some reason manages to do well, which is to move quickly into the screen. Here's a bilaterally symmetric robot, which may have potential, but doesn't go anywhere, so was quickly deleted from the population. You can see, again, in an evolutionary algorithm, most of the candidates are non-functional. Here's sort of a non-obvious but functional design. Okay. So what are the advantages? A research question which we will explore is, what are the advantages of automating the design of the body plan along with the controller compared to just manually designing the mechanical structure and optimizing the design of the controller? Yes?
You could save the time that it takes and like the thought it takes to actually design the physical robot.
Exactly. If we can automate more of the design process, it should speed things up, right? Human engineers are incredibly talented, but it still takes time to design and verify a mechanical structure. Yes?
Are you able to take the evolutionary algorithm and push it in a direction that you sort of want it to go down?
Can we ensure that can we push the evolutionary algorithm down the path we want it to?
You have a lot of these multi-legged vehicles.
Yep.
So you're obviously trying to get towards a centipede kind of motion. Can you just say, look at this, try to figure out how this works, and then evolve past it if you can?
That's a great question. So again, this is something we'll explore later in the course, which is how much detail do we give the evolutionary algorithm about what we want? And it turns out that there's a gradient. We can say, we just want a fast-moving robot. That's it, right? We can be as vague as we want, which has its advantages and disadvantages. Or we can say, we want something that's bilaterally symmetric. The left side of the body should look exactly like the right side of the body. Or we can go further and say, we want a centipede-type structure. Here's some videos of motions of actual centipedes. Do something like that, right? We can be more or less specific, and there are pros and cons to where on that gradient you pick your point. We'll talk about that again later. Okay, good question. Okay, so this idea of expanding the evolutionary algorithm to include the body, this is sort of a step along the path of the history of AI, which we'll get to in a few minutes. Most of the early decades of AI was dealing with creating a non-embodied AI, like a neural network. So here's a little cartoon picture of a neural network where the gray circles are meant to represent neurons and the arrows are meant to represent synapses. We would like this neural network to take as input a photo, for example, and output a signal indicating whether the neural network thinks there's a cat in the image or not, right? Sort of standard non-embodied AI approaches. If we have a neural network that's doing an okay job of recognizing cats in photos, and we alter the weight of one of these synapses, what's the impact on the ability of the neural network to recognize cats in photos? Does it get better? Does it get worse? Does it get worse by a lot or just a little? There's a lot of early work in AI about fixing the architecture of the neural network and then tuning some of the parameters. Was there a question? No? Okay. In just a few years, now that neural networks research has made some progress, there are now questions about, can we automatically design or tune the architecture of the neural network? So now, instead of the human fixing the architecture and allowing the computer to alter parameters, can it start to add and remove neurons and synapses? What we're going to talk about in this course is sort of the next step in that progression, which is if the neural network is inside a wheeled robot, for example, what's the right choice for the shell of the neural network controller? Should it be a wheeled robot, a legged robot? Depends on what we want the robot to do. Biggest open challenge, which no one has solved yet, is can we create an evolutionary algorithm or some other learning algorithm that's able to tinker with all three systems at the same time. The architecture of the mechanical structure, the neural architecture, and the parameters describing these elements themselves. Right? There are advantages to trying to take as much of a step back as possible and automate as much of the process as possible. But as you can imagine, the more hands-off we are, there are more ways for perverse instantiation to come into play, which is the idea that the AI or the evolutionary algorithm comes up with solutions that work, but not in the way we wanted them to work. Right? Okay, again, we'll talk about that later. Okay, why else is it interesting to use evolution to design machines? Because evolution has already demonstrated that she can do this very well. Mother Nature has been creating extremely sophisticated machines for 4.5 billion years, assuming you're not religious, without any external supervision. So it's possible in principle, as nature has shown us. So could we replicate this process? Again, maybe at a smaller scale, inside a computer. There's another argument for why we might use an evolutionary algorithm rather than other optimization methods. Right? Evolution is definitely not the most efficient search process, but given enough time and resources, it can often find very, very good, but not optimal solutions. I'll probably repeat this many times in this class, but it's important to remember that evolution is not an optimizer, she's a satisficer. She will come up with solutions that are just good enough to do what's needed, but not in an optimal manner. Unless, when we specify, when we're very specific about what we want the evolutionary algorithm to do, we say we want a good solution and we want it to be at least as efficient as this, whatever we mean by efficiency. Okay. Final reason why you might want to use an evolutionary algorithm is this idea of supervision. So what do we mean by supervision? Let's start with an example. This is another early experiment that I was involved with where we were evolving controllers for a biped robot in simulation. Here's a partial solution. Okay, I think we got to about 11 steps, and this was running on machines for a very long time. We used a neural network controller in this case, but for argument's sake, let's imagine we use this matrix type of controller that we talked about before, where every row in the matrix corresponds to one of the motors inside the robot, and every column represents some time period. In this case, we have rotational joints, not pistons, so joints that are like your elbow or your knee joint. So a +1 maybe means extend the joint, and a -1 means flex the joint. Imagine you have, yes, question?
Is it still typical to just, when we're like developing an algorithm to describe behavior, say exact time period, do exactly this, or is it more sensory based?
It's definitely not like this, but it's easier to think about this than it is to think about neural network controllers. Yeah, okay, this is just sort of for argument's sake. So imagine we're at this point in our optimization process. We have a matrix which causes the biped to take 11 steps and then fall over. And imagine the computer or someone or something gave us some supervision. It said, aha, I know why the robot fell over. It's because this element in the matrix is wrong. Wouldn't that be nice? It turns out that we usually don't have that supervision. We just know that the robot fell over at 11 steps, but it's not clear where in the controller or even where in the body. If we were to make a change there, the robot would now take 12 steps or 14 steps or 100 steps. We don't have good supervision. So if you're familiar with supervised learning or unsupervised learning, if you've taken an AI class, evolutionary algorithms are known as semi-supervised algorithms. Why semi-supervised? Well, there is some supervision, there is some feedback coming back, which is the number 11. The robot took 11 steps, right? So a robot that takes 13 steps or 2 steps is better or worse than our 11-step robot. So we're getting some number back, but it doesn't give us a lot of information, right? It doesn't tell us where the problem is. It just tells us for this solution, here's how good it is at solving the problem, right? So it's only semi-supervised. We, or the evolutionary algorithm, has to go in and make changes and see whether that improves things or not. In the case of the neural network that is recognizing cats in a photograph, it turns out that's a supervised learning problem, meaning it is possible to actually identify if the neural network misidentifies cats in an image, or a set of images, it is possible to actually automatically go in and find where the problems are in the neural network. The earliest and simplest way to do this is the backpropagation of error algorithm, for those that have heard of backprop. Not important for our purposes, but just situating this in the supervised learning literature. Yes?
So would it be right to say that if you keep on repeating the same algorithm,
Yep.
evolve it, that you would have different results? Because you said that it takes 11 steps, but you cannot say that the 11th step is the wrong one.
That is a great question. So let's imagine our evolutionary algorithm has got to this point. It's discovered a neural controller that gets the robot to take 11 steps. What happens if we keep running the evolutionary algorithm? Can we guarantee that the evolutionary algorithm will eventually find another controller that gets the robot to take 12 steps or 14 or 100? Turns out that, at least for evolutionary algorithms, no one has been able to figure out how to guarantee that it will. We could run our evolutionary algorithm for the rest of the lifetime of the universe, and it may never find a controller that gets the robot to travel any further. It doesn't mean that somebody won't someday figure out a way to guarantee that they will. Yeah. So again, what we're going to spend some time in this course doing is thinking about how to apply evolutionary algorithms in the right way. And we'll take a lot of inspiration from nature, that at least we increase the probability that the evolutionary algorithm will continue to make progress the longer we run it. So that's a disadvantage of evolutionary algorithms. They can't promise us that we'll find better solutions. There are other optimization methods out there. They don't work for body plans, but they work for naked neural networks, where you can guarantee the algorithm will make improvements. Question?
So back to kind of his sensory question, like if, say, this robot had like arms as well.
Okay.
And like, have you ever done anything in these simulations where it would like sense like, oh, there was an impact on my body, which means I fell over, and then like it responds to that in some way? Like, does it take in like sensory information throughout time, or is it more like a...
So a good question about sensory feedback. We haven't obviously talked much about the details of these neural network controllers. When I mention a neural network controller, that's short form for a neural network that is receiving as input not photographs with or without cats. It's taking as input sensor data from the robot itself. So in this specific example, the neural network controller was getting information about pressure on the soles of the feet, and also information about the rotation of the upper body. So the robot could, in essence, feel pressure on its feet and feel the movement of its upper body. And those sensor values are feeding into the neural network, which in turn is changing the movement of the joints of the robot. Now, whether pressure sensors and joint angle sensors were the right choice here, I don't know. We decided that. Maybe it would be better for the evolutionary algorithm to decide what are the right sensors for this robot given this problem. Yeah. Okay, so this was some very early work that I and some others did on this problem. There's some other great, more recent videos out there on exactly this. This was one from a few years ago. In this case, they're fixing the body plan, but they're evolving the muscle placement inside the body. Why would they do that? It turns out that the neural network controllers they find are adaptive to changes in the body. This was actually a computer graphics project. You can obviously see the entertainment quotient here. This is a particular type of evolutionary algorithm, and a nice visualization of how an evolutionary algorithm works. Okay, let me speed up the video here a little bit. So here in the fitness function, they were asking for movement at a particular velocity. So a little bit more detail in the fitness function. Someone was asking about being hit by objects. So robustness to changes in the environment. They could also use a joystick and control the movement. It's had a lot of social media interest when it came out. Someone quipped, "This is what my Monday feels like." Okay. I'll leave you. You can watch the rest of this video at your leisure. Okay. Okay. So, and now for something completely different, let's switch and talk about the history of AI, which will again allow us to situate evolutionary robotics in the larger landscape of AI and robotics. Okay. Since this is a history, we're going to do this in chronological order. We're going to start with cogito ergo sum, who was said by Descartes, right? Okay. So I think, therefore, I am, mentioned by René Descartes in his Discourse on Method back in the 1600s. So a long way back for us to start the history of AI and robotics. Just a little logistics note here. In Lecture 2 and all the rest of the lecture notes, from time to time, you'll see an empty red box. That's just, again, a little prompt to you to annotate your slides. In your version of the slides, you won't have Discourse on Method. Just a prod to you to fill in these boxes as we go. Okay, so why are we starting the history of AI with I think, therefore I am? Seems like kind of an odd place to start. For those of you that have not read Discourse on Method, it's a pretty dense read. Descartes wanted to try and establish once and for all what is true. Among all the vagaries of life, all the things that it's hard to verify, is there anything at all that we can be 100% certain exists and is real? It's a very intricate argument. I am doing it a great disservice here in abstracting it down to a single slide, but for our purposes, the argument goes as follows. If you're a 16th century philosopher or a 21st century student, you might ask yourself, do I even exist? How do I really even know? Today we might say, am I living in the Matrix? Who knows? I don't know, right? There's a lot of uncertainty out there in the world. I don't know if you all exist. Maybe everything's an illusion. I don't feel like I can stand on any solid ground. So I start by asking the question, I don't know about everything else, but let's at least start with me. Do I exist? Well, in this short sentence, there is one word, I, this interesting pronoun. I don't know exactly what this I thing is, but it seems to be the thing that is asking the question. So that thing, there is something that is asking the question. I can't be sure what it is, but if it wasn't there, there wouldn't be the question, and the question is there, so the I exists. Again, it sounds a little circular. There's a lot more to it, but at least for Descartes, it led him to the realization that the I exists, which he would have said is the soul. Today, most of us would say the I is the mind or the brain. That subjective part of you, right? The voice in your head, that thing is real. Now, the body, the thing that carries it around, even that I'm not so sure about. Why? Because I don't have any direct way of interrogating it. There are these signals that are coming in from out there in the world. Some of them feel painful, or there's colors and shapes coming in. I think they're coming in through my eyes or my skin, but I don't know. They're just sensations that are arriving at the eye. So that's the only thing I can really be sure of. The body and everything beyond the body, I don't know. So what that means then is if I'm sure the eye exists, but I'm not sure that the body exists, then clearly they're very, very different creatures. So the soul, or the mind in the body, the mind or the brain, and the body are different. That was one of Descartes' conclusions from Discourse on Method, which led to this idea of Cartesian dualism, or what some of us think of as a major problem. Cartesian dualism exists all through Western thought, this idea that the subjective self and the physical body or the physical world are separate things. And it turns out that Cartesian dualism pops up in lots of places aside from just abstract philosophy. It pops up even in things like AI and robotics. You can see that Cartesian dualism pops up in AI robotics because I'm using the word and, AI and robotics. Even the study of intelligent machines is broken into two very different camps, one that focuses on neural networks, and one, the roboticists, which tend to focus on mechanical construction. There's very little feedback between the AI and the robotics community, right? Kind of interesting. We'll actually see Cartesian dualism cropping up quite a few times, even just in our discussion of evolutionary robotics. As I've already told you this morning, in evolutionary robotics, we want to try and close the gap between the neural network controller and the body of the robot by having the evolutionary algorithm co-optimize both of them together. Again, if we look at biological evolution, Mother Nature doesn't respect the distinction between mind and body. Evolution mutates and alters nervous tissue and non-nervous tissue simultaneously, right? She doesn't respect the boundary. The only people that respect the boundary are members of or children of Western thought like ourselves, because of the inheritance of Cartesian dualism. So we're going to spend a lot of time in this course trying to fight against this idea and think about how to build these two subsystems, which are not really separate subsystems, together. And as you'll see, it's hard to do. We are often pulled by Cartesian dualism. The living philosopher Daniel Dennett, if you're familiar with Daniel Dennett's books, refers to this as Cartesian gravity. It's invisible. Most of the time we don't see it's there, but it is always pulling on us. Okay, so let's jump 3 centuries forward into the 20th century, early 20th century. Typically, when we're talking about computers or AI or even robots, we tend to think information or input first, processing, and then output, right? If you think of yourself as a machine, you often think about signals from the environment falling on your sense organs, like your eyes and ears, gets sent to your brain chews on that sensory information for a while, maybe combines it with memory, and then sends commands to your muscles, and you act. It's how most of us think about behavior in humans and animals, and especially computers. Why? Again, thanks to some important thinking by Alan Turing. Alan Turing, back in the 1930s, proposed the Turing Machine. Most of the computer scientists in this room should be very familiar with the Turing Machine. If you haven't heard of it before, it's basically a thought experiment. A Turing machine is any machine that is in contact with a tape. Tape in quotation marks. Tape could be anything really, but it's something that contains information. The machine reads the symbol at the current location on the tape. That's the input. It's reading something off the tape. In the early days of computers, there was a literal physical tape. Depending on the machine's current state and the symbol that had been read, depending on that information, the Turing machine would decide to act. It would either update its own internal state and or write a new symbol to the tape, so act on the environment, and or move the tape forward and back, or move itself forward and back. Seems like kind of an odd machine. The advance that Turing made back in the early 20th century was to prove that with a long enough tape, you could get this very simple machine to perform any computation you could imagine. No matter how complex it was, given a long enough tape and enough time, the Turing machine could solve the problem. That was mind-blowing for mathematicians at the time and led a lot of people, including Turing himself, to imagine, could we actually build one of these hypothetical Turing machines in reality? Could we make a physical machine which reads and writes symbols to a tape and does computations for humans without humans being involved at all, which sounded like a crazy idea. But as you all know, in the late 30s and early 40s, Turing and his colleagues actually managed to do that, which ushered in the computer age, right? Okay. Obviously, this will be very important for robotics as well. Let's move 2 decades forward to 1956. In the summer of 1956, about a dozen scientists got together just down the road at Dartmouth College and spent the summer, now that computers existed, they wanted to not just build computers, but build smart computers. And in the spring of 1956, they sent in a proposal to the government to do this. We proposed that a 2-month 10-man study, this is obviously the 50s, of a 10-man study of artificial intelligence be carried out during the summer of 1956. So it was the first time artificial intelligence had actually ever been written down. This is when the actual term was coined. And we proposed that the study will proceed on the basis of the following conjecture. Every aspect of learning or any other feature of intelligence, in principle, we can precisely define it. If we can precisely define it, it becomes a computation. And if it becomes a computation, we can run it on these newfangled physical Turing machines, and we can simulate any intelligent behavior. Some went so far as to think that you could reproduce intelligence, not just simulate it, which again we'll discuss later. An attempt will be made to find how to make machines use language, form abstractions and concepts, solve kinds of problems that now only humans can do, And also, by the way, they'll also be able to improve themselves. So if you, Uncle Sam, give us the money to do this, we'll spend the summer doing it for about 2 months. We should be able to solve all these problems. We think that a significant advance can be made in one or more of these problems if a carefully selected group of scientists does this, and that carefully selected group of scientists was, of course, meant to be the scientists who wrote this proposal. The government gave them the money. They spent 2 months doing this. How did they do? Not too well, right? So where are we now? Is this 70 some odd years later? It's taking a little bit longer than 2 months, right? We're still working on it. For most of that 70-year period, we made little to no progress. But last decade, the 2000s, we actually did make that. From 2006 till now, we've actually started to make some progress, right? We have some machines that at least can recognize patterns. They can see cats in YouTube videos. I would argue that they can't use language yet. There are others that say they can. We can argue about that one. But we certainly don't have HAL or the Terminator or Commander Data or sort of the machines or the robots that these scientists had in mind, right? Why is this such a notoriously difficult problem? And why were these scientists so fantastically wrong in their assumption that they could do this in 2 months? Kind of an interesting idea, right? Anybody have any ideas? Why did it seem so easy at the time and it's turned out to be so hard? What? The computational resources? Exactly. So that's a great point. So there's sort of two issues. One is computational resources, right? The human brain has 10 to the 11 neurons in it and 10 to the 14 synapses. Most computers now are at least starting to reach that level of complexity, but the computers available in 1956 certainly weren't, right? So there just wasn't the computational resources available at the time. But the bigger conceptual challenge, which is still holding us up, even now when we have pretty sophisticated computational resources, is the fact that we cannot precisely describe what cognition is, right? And this kind of goes all the way back to Descartes, right? Descartes said there's this I, this thing inside my head. I don't know what it is and I can't precisely describe it. Neither can we, at least not yet. So if we can't precisely describe it, it's hard to simulate it or create it. The idea in evolutionary robotics is, okay, if we can't describe it, at least we can describe the behavioral effects of it. We want something that moves around, is robust to changes in the environment. You, evolutionary algorithm, figure out how to do it. We know what it is, we just don't know how it works. So maybe we can sort of reverse engineer it using evolutionary algorithms. Whether we'll be successful, who knows? We'll give it a try. Okay, so here's a list of the scientists that were involved. Anybody recognize any names on this list? Minsky, which we'll talk about Minsky today. Unfortunately, he was involved in the Epstein case and was a known child sex offender. So it's important to mention his name. He is a pioneer in AI, but that will be the last we'll talk about him in this course. Anybody recognize any other names on this list? Claude Shannon, for the mathematicians in this room. Claude Shannon gave us the definition for information. We obviously live in the information age. What does information mean? What is the definition of information? Before Shannon, like intelligence, it was hard to precisely describe what information was. Shannon managed to do so, which is obviously an important contribution to AI and robotics as well. Alan Newell, another important pioneer in AI. John McCarthy was the chair of this committee, the organizer and the inventor of the term AI. As I mentioned, Minsky was the co-founder of the MIT AI Lab, which still runs today, known as the CSAIL Lab, CS and AI Lab. If you ever make it to Cambridge, it's great to go visit the building, probably one of the meccas for AI research still today. Herbert Simon was an economist, kind of an interesting person to have involved in this. We'll talk about Herb Simon again later. If you've ever taken a course here with Professor Skalka in the computer science department, Professor Skalka was Herbert Simon's last PhD student. So there's a direct linkage from Professor Simon to us. As you can see here, he was an expert in decision making, which is obviously an important component of intelligence. If you're interested in the history of AI, it's a good exercise to go and look up these other names and find out what contributions they made to early work in AI. Okay, so let's just take a pause from our history here to talk about some of the goals of artificial intelligence. This is a little snippet taken from our book. What are we actually trying to do in AI? Well, different people are trying to do different things. One thing you might want to try and do by building AI and robots is not strictly to focus on creating artificial intelligence, but use the effort of creating AI to learn more about natural intelligence. As we just mentioned, we can't precisely describe intelligence because we don't understand it very well, right? The brain is the most complex artifact known to our species. It's very complex. No one really understands how it works yet. There's obviously a lot of science dedicated to understanding the brain. Robots and neural networks are two recent new scientific instruments to try and understand the brain. If we can build artificial machines, artificially intelligent machines, we would then have two species which are capable of abstract cognition, humans and machines. Machines may implement intelligence differently from us. Who knows if we ever get there. If they do, we might see common patterns across these two species. At the moment, there's only one species that exhibits general flexible intelligence, and that's us. So it's hard to know anything general about the general principles of intelligent behavior. The only example we have is us, right? So if we can create other examples of things that are capable of intelligent behavior, we might be able to distill out from all of them general principles of intelligent behavior. That would be extremely exciting. Finally, as we're doing this, we can feed this back into machines and try and create intelligent artifacts. We haven't learned too much yet. However, one of the things we've learned is for certain kinds of maybe simple behaviors, but at least behaviors that are on the road to intelligence, you can get away with very, very simple brains. Here's an example of one of these creatures. This is a Bratenberg vehicle, and we'll talk about Bratenberg vehicles later. It's basically just a box. It's got two wheels on the back and two light sensors on the front. One sensor front left, another sensor front right. If we place a light source to the front left of the robot, there is more light falling on the left sensor, and this robot will turn towards the light and chase after it if allowed to. Why? So I've described the two wheels here and the two sensors.
You'll have greater acceleration or movement on the right side or opposite side where the light is.
Exactly. So you'll see these two wires inside. You can think of these wires as synapses that connect the left light sensor to the right wheel, and a second synapse or connection from the right sensor to the left wheel, so that if there's more light falling on the left sensor, the right wheel will turn faster than the left wheel, and it will turn slightly towards the light, right? So if you then take a flashlight and start moving around the room, the Bradenburg vehicle will chase after you. You may or may not consider that intelligent behavior, but it's at least on the road to intelligence. And you can do that without the robot needing to recognize the flashlight in its visual scene. It doesn't need to know that it's a flashlight. It doesn't need to know that the flashlight is on. It doesn't need to calculate trajectories and differential equations to figure out how to move towards the light. It is a very, very simple, internally simple creature. So we've already learned something from trying to build machines that chase after light sources, which is that at least for some behaviors, things are more simple than we thought. For recognizing patterns in images, understanding and generating language, things seem to be harder than we thought. So some things, it seems, are easier and some things are harder. Lego a few years ago made an actual robot kit called Lego Mindstorm. Some of you may have played with these as kids. You can actually build a Bradenburg vehicle out of Lego Mindstorms. I guess the link to the video is broken, but if you go to YouTube and Google Bradenburg vehicles, you'll see a lot of them made out of Lego. Pretty simple. Okay, let's come back to our historical discussion. We're going to jump from the 50s to the 60s. In the mid-1960s, we enjoyed the first AI summer. So you may have heard the terms AI summers and winters. The idea here is that, again, since 1956, when people started working on AI, there was a lot of optimism and there seemed to be a lot of progress. People got very excited. After a few years, everybody kind of calmed down and the limitations of the technology at that time were recognized. People were sort of turned off, and that the overhyping of the progress caused a backlash. Funding was withdrawn, and we switched from an AI summer to an AI winter. That has happened 3 times so far. As you're probably aware, we are now in the middle of an AI summer. People are still very, very excited about AI. And for those working in AI, we're particularly worried about whether we're going to enter an AI fall, right? Can we keep this up? Are people and funding agencies going to continue to be interested in AI and robotics? We'll see. Okay, why did people get excited in the mid-1960s? One of the reasons was ELIZA. This was the very first chatbot. ELIZA was meant to be a computer psychotherapist. You could sit down at a terminal and she would say something like, I am the psychotherapist. Please describe your problems. Each time you're finished talking, press return twice. The human says, I have a terrible headache. And ELIZA said immediately, maybe you should consult a doctor of medicine. I'm a psychiatrist. Imagine you were an average person in the mid-60s. You had never used a computer at this point. You enter a lab and you're put in front of this crazy gizmo, and it starts talking to you in this manner, right? For most people, they were convinced that human-level intelligence not only was imminent, but it was already here. We jumped from these wartime computers that had been used for calculating the ballistics of missiles to a computer that could casually chat with you and help you with your psychological issues. Amazing, right? If that could be done in less than 10 years, what's possible? Of course, this was basically a hoax. Not really a hoax, it was also a demonstration that, again, you could convince a lot of people that you had a very smart machine on your hands, when that machine did nothing more than apply a set of very simple if-then-else rules. So ELIZA came pre-programmed with a dictionary. She would scan a sentence, and most people that talk to a psychotherapist say things like, I verb proper noun. I'm fed up with my headaches, for example, right? So she would recognize pronoun, verb, proper noun. And one of the most successful if-then statements in ELIZA is to just answer a question with another question, which is to rearrange the verb and pronoun and proper noun into Why do you, verb, proper noun, question mark, right? With that and a few other statements, you could get some pretty sophisticated chatbots. What are some other simple rules like that that you could imagine are in there? I, verb, noun. Why do you, verb, noun? That's one.
Can you elaborate on that?
Can you elaborate on that, right? Canned responses. I'm sorry, I didn't understand. Could you explain in more detail, right?
Someone says nearly the same thing twice, to have a special response calling them out on that.
Exactly. You're repeating yourself. We've already gone over this material, right? So a lot of those kinds of things, which human psychotherapists also psychologists rely on, right? It's not necessarily a bad strategy. However, if you go online today, I don't know what the current state-of-the-art chatbot that's out there. They do okay for a while, but for most of us, it doesn't take long to realize that you're talking to a computer and not a fellow human being. That, at least personally, is the reason why I feel we haven't made much progress on natural language processing and generation. Okay. So, again, a lot of hype that eventually died down. Why are we talking about chatbots? The reason why is that chatbots, or at least their early version, was an argument in Turing's case about intelligence. So in Turing's day, and throughout the 50s and into the 60s, there was a lot of argument about the actual definition of intelligence. Turing felt we will never have a definition of intelligence. Instead, the best we can do is consider something or someone intelligent if they act intelligently. So Turing proposed the Turing test, which was place a human being at a console and tell that human being that there's a 50% chance that on the other side of the terminal, there's a computer program or another human being, but we're not going to tell you which. And we want you to determine, to guess correctly, are you talking to a computer or are you talking to a human being? And if you could create a computer program that would fool most people most of the time, that's an intelligent machine. That's the best we can do according to Turing. Yeah? You've probably heard of the Turing test. Hollywood loves the Turing test. Again, I don't have time to play the video. This is a clip from Blade Runner. The Turing test played an important part in the original film of Blade Runner. If you have not seen Blade Runner, it is mandatory homework watching for this weekend. You have something which, as you can imagine, turns out not to be a human, being asked to conduct a Turing test that is administered by a human interrogator. Things don't end up very well for the human interrogator. If you haven't seen it, please do watch it this weekend. Okay, mandatory watching. Okay, so according to Turing, we could not define intelligence, so we'll have to just call things intelligent if they act intelligently. In the 1980s, early 80s, John Searle, a philosopher, had a problem with that. He said, that doesn't sound good enough. And in order to prove his point, Searle created a thought experiment, as philosophers tend to do, to disprove the utility of the Turing test. So the Chinese room is meant to be a counterexample. It is something which seems to be acting intelligently, but is definitely not intelligent. It's something that passes the Turing test, but is not intelligent. Okay, here we go. So in the Chinese room, inside the room itself is an English speaker. The English speaker cannot read Mandarin, cannot speak Mandarin, doesn't understand Mandarin at all. Outside the room, there are two Mandarin speakers. They write a very complex question in Mandarin on a piece of paper, and they pass that question through the slot in the door that is taken up by the human speaker on the inside. The human looks at the Mandarin on the piece of paper and sees nothing but a bunch of squiggles and squaggles. Means nothing to the person inside the room. However, in front of this human in the room, there's a large book, and that book is written in English. And that book says, if you see the following squiggle squoggle, on a new piece of paper, write a different squiggle squoggle, write this one. If you see this pattern, write that pattern. If you see this pattern followed by that pattern, write this pattern, then that pattern on your new piece of paper. It had a whole bunch of if, then, else rules written in English. If the person inside the room followed those instructions honestly, they would write a whole bunch of Mandarin symbols on this piece of paper, not understanding what they're doing, and passing that piece of paper back out the slot in the door to the Mandarin speakers on the other side. And if they read it, and if this book is big enough, in theory, these Mandarin speakers outside the room should be convinced that there is someone inside the room that is able to read and write in Mandarin. So far, so good?
Wouldn't the time that it takes for a non-Mandarin speaking person to go through giant book of rules sort of preclude that they actually spoke Mandarin?
Possibly, right? So obviously this would take a huge amount of time, right? Assuming it's even possible. This book might have to be infinite size, who knows? So there are other human elements at play here. If we were to actually do this with people, that might convince the people outside the room that there's no one inside the room that speaks Mandarin. However, you may have recognized in this thought experiment that this is actually riffing on some ideas we've already talked about, right? So the person in the room is supposed to be like Eliza or a chatbot, where the chatbot itself is dumb. It's just replacing symbols with other symbols without understanding what those symbols mean. And the person and the pieces of paper is also a Turing machine. Read and write symbols, right? So the Chinese room as a whole passes the Turing test. It seems to be thinking, seems to be intelligent, but there is nothing intelligent about the Chinese room. Of course, there's a human inside that's intelligent, but they're not using the intelligence we're interested in, which is understanding Mandarin. There is a person who wrote this book, presumably. That person was smart, but they're not in the room at the moment, right? It's the room itself which is on trial. Is it intelligent or not? It passed the Turing test, and it's not intelligent. So for Searle, that was it. He had defeated Turing and showed that the Turing test was flawed, right? Now, you may or may not agree with Searle. You may or may not agree with Turing, but it's an interesting exercise from the history of AI about how difficult it is to define intelligence. There are others that felt that actually the Chinese room vindicates the Turing test. I am one of those people. Why? Because when you look at the Chinese room, it's clearly intelligent, but the elements themselves are not intelligent, right? How is that unlike a human brain? An individual neuron or an individual synapse is not intelligent. A neuron doesn't think. A synapse doesn't think. A small piece, a bundle of neurons and synapses doesn't think. But I look at most of you, and depending on the responses you give me to your questions, I think you are intelligent. I think that you are intelligent, even though the components inside your head, those individual components themselves, may be unintelligent. What does it matter whether the unthinking elements are neurons or synapses or non-Mandarin speakers or books or computer chips or frog cells? Maybe it doesn't matter what those dumb components are. If they're put together in the right way, that's what causes humans to attribute intelligence to that collection of elements.
Doesn't it have to pass the test because it beats that 1956 trial that they set up where you had the infinite supplies and you had the human thought and the both of them?
Possibly. You could view it that way.
They did everything that they were going to do in that period. They just example
Yeah, it could be, right? So we're in the land of philosophy. We can argue one way or the other. I think we'll leave things there for today. You have a quiz due tonight. You have assignment 1 due Monday night, and I will see you again Tuesday morning. Thank you.